Hi, folks. This is Maria. I'm sorry I can't be there with you today. Any coughing fits, I'm going to do my best to edit out, but just be aware of that. That might be something that occurs. All right. So you are learning about special double replacement reactions today. Now, just to remind you what double replacement reactions are, remember that's where essentially when we're thinking about two ionic compounds, both of them are aqueous reactants. They're always, always, always aqueous reactants. And they're going to switch cations and anions. So that's all that I want you to keep in mind when I'm going forward and thinking about this. All right, I also already told you about the two different types of special double replacement reactions, precipitation reactions and neutralization reactions. Remember precipitation reactions, just where a double replacement reaction produces a solid, and a neutralization reaction where you have an acid and a base, which are always in the form of HA and then BOH in this class, and they end up producing water and a salt. Now, for the precipitation reaction and the neutralization reaction, I highlighted two of the different things. Take a moment, see if you can figure out what about it that was special, why I highlighted those. Now that you've taken a moment and taken a look at both of these equations, you might have noticed that the things that I highlighted are the only things in each of those equations that aren't an aqueous reactant or product. So just something to keep in mind. So therefore, when we're talking about these different types of special reactions, we use two different types of equations. One of these is called a complete ionic equation. Now, a complete ionic equation is just a representation of what's actually happening in solution. So I want you to think back to your particle level diagrams. This is where they're super useful. So if we're using the example that I presented before, the complete ionic equation would be this bullet point here, where I'm looking at silver nitrate, which remember, I know if that's in solution, it's broken apart, right? It's an ionic compound in solution. Same sort of thing for the magnesium chloride. If it's an aqueous compound and, if it's an aqueous reactant, that means again, it's broken apart in solution. But then I end up forming the solid at the end, and I know that solids are more organized and not as dissociated in solution. And the magnesium and the nitrite ions are more floating around when we're thinking about this. Okay, so that's helpful for when we're thinking about what's happening in solution overall. But you probably kind of noticed the stuff that's sort of important for identifying whether this is a precipitation reaction or not is just this, whether it forms like a solid or not. So that's why we have net ionic equations. It's where you have any spectator ions, so ions that are in the same form on either side of your complete ionic equation. They've been removed. Only the important stuff is left. So there's two silver ions and two chloride ions from before. Well, again, they were in aqueous format, so they should just be floating around in solution. And then they end up forming the silver chloride. Cool. Awesome. Just something to keep in mind as we're going forward. So part of what you're going to do today is identifying different types of special double replacement reactions. So here's sort of your general rules of when you're going through and doing that. You start by writing out the balanced equation, and you're going to check solubility rules. That's really important, especially if we're trying to figure out if a precipitation reaction occurs. Now, if you're like, what solubility rules? That's fair. We haven't used them yet, but they're on the back of your periodic table. It's in the charts where it's red and blue towards the top half of the periodic table. So you're going to check those solubility rules to figure out whether you are forming a precipitate or not, something that's very helpful to know. And then you're going to write out the complete ionic equations. Only aqueous ionic compounds are going to break apart in solution. So if I have something that I've identified as a solid, remember that does not break apart in solution. That's found, at the bottom of my beaker when I'm drawing my particle level diagram. I will make a quick note here with the complete ionic equations. Yes, they look really long. And yes, for pages 33 and 34 only are the only times that I'm going to ask you for the complete ionic equation. They're really helpful, mostly just for when we get to step 4. So that's the only reason why I'm going to make you practice with them for now. And then I promise I will stop making you write out the complete ionic equations. The third thing that you do is eliminate any spectator ions. Remember, that's just where you have ions in the exact same form on both sides of your equation. And then you write out your net ionic. So if all those ions were actually spectator ions, it's just a normal double replacement reaction. There's nothing like special about that particular double replacement. If you end up in your net ionic forming a solid, it's a precipitation reaction. And if your net ionic formed water, it's a neutralization reaction. Just something to keep in mind. All right, so we're going to do some practice on this. So if you want to turn to page 33 in your packet, this is the first problem that's in your packet. So it's written out in your packet as calcium acetate reacts with potassium carbonate to produce. So if I'm writing out calcium acetate reacts with potassium carbonate to produce, remember, since it's double replacement, my cations essentially switch spots. That means my potassium should be matching up with my acetate, and my carbonate should be matching up with my calcium. So just something to keep in mind. So the first thing that I'm going to want to do before I do anything else is balance the equation. So I can tell already when I'm going through, and I've written my ionic formulas correctly, remembering things like calcium is 2 plus, acetate is -1. So therefore, in order to have a ionic compound that has a charge of 0, I need 2 acetates. If I wrote out my potassium carbonate, remembering that there's 2 potassiums because of the fact that carbonate has a 2- charge. And then over here, because potassium has a +1 charge, acetate has a -1 charge, calcium has a +2 charge, carbonate has a -2 charge. Just something to keep in mind. You may need to go back and review those ionic compound naming rules. I've also posted the link if you need it for my video back on ionic naming. So just something to be aware of. So the first thing that I got to do, balance this equation. I can already tell that my acetates and my potassium are out of balance. So if I balance it, I just put a 2 in front. There we go. Perfect. I have a balanced equation. So, but I have these question marks here that I got to fill in. Remember, there's really only 2 options that I have for when I'm thinking about ionic compounds. It's aqueous or it's a solid. So take a look, pause it for a moment here, see if you can figure out which is which. Is there a solid? Are they both aqueous? What's going on? Take a look at the rules on the back of your periodic table. Right? Now that you've taken a look at the rules on the back of the periodic table, you figured out that potassium, because it's potassium acetate, any of the acetates are pretty darn soluble when we're thinking about this, but carbonates are not so soluble, especially with the calcium added to it, so this would be a solid. All right, great. So now we have a balanced equation where I know the different states of everything. So the next thing that I would do using that balanced equation is write out my complete ionic equation. Now remember, that means I'm essentially just writing out the complete ionic equation where I have my ions separated in solution. So here's the products. I've written out, remember, since this is aqueous, that it's going to split into 2 different things. I've got my calcium that it splits into, and there's 2 acetates that it splits into. Again, it's aqueous, so it's going to split into its 2 different pieces. I've got 2 potassiums and 1 carbonate. Now, if you needed to take a moment, maybe predict of what's going to happen here, pause the video, see if you can come up with it yourself. All right, so if you came up with this, you hopefully came up with that this, because it's aqueous, again, is splitting into pieces. Now remember, this is a solid. If it's a solid, it is not splitting into pieces. And so that's a big part of what you're doing when going through. All right, so I've written out my complete ionic equation. So let me do my next step. I'm going to write out my net ionic equation, and I'm eliminating any spectator ions. So how do I tell what are my spectator ions? Remember, that's just what's the same exact way on both sides of the equation. So I would say, if I'm looking through, well, calcium, that's not the same exact way. It's found in a different form on this side. But I have acetate, that's aqueous on both sides. Potassium, that's aqueous on both sides. And carbonate, that's found in a different form on this side of the equation. Just something to keep in mind. So I would eliminate those. And then my net ionic equation is essentially just everything without the eliminated stuff. So my net ionic in this case would be calcium 2 plus, oops, sorry, with carbonate 2 minus forming calcium carbonate, the solid. All right, great. So I formed a solid, so therefore this is a precipitation reaction. You will find that most of the problems on pages 33 to 34 are precipitation reactions. Now that's not true for all of them, so be careful when you're going through. I do have a quick note on the neutralization reactions. Remember that neutralization reactions, that's just where I end up forming, always water is one of the things that I end up forming. You can also figure this out just by doing the reactants, if you're looking at the reactants. If I look at the general format, I'm always going to see something with a hydrogen in the very front, and then I'm going to see something with a hydroxide group in the back, and then if I always see water, that would be something as well. But you can actually just figure this out just by the reactants. There is, in fact, at least one neutralization reaction on pages 33 to 34. All my answers are posted on campus, so you're welcome to go through, take a look, but I would try it first. All right. Feel free to email me any questions, and I'm happy to work with you more on any of these. All right.